Today we'll start having a fairly good look at topological spaces based on our previous developments of set theory. And as I announced last time, topological spaces, or establishing a so-called topology on a space, I'll define in a second what that is, presents the weakest structure you can establish on a set in order to have the two very important notions of convergence and of continuity. Convergence of sequences, of points on a set, and continuity of maps between two topological spaces. Now, the definition I'm about to give is at first sight rather abstract on the downside. On the upside, it's extremely simple. And this definition is the result of a historical development, and I'll comment occasionally on that. So just take the definition as the simplest definition that, after all, mathematicians found to be of use in order to define topologies. So the definition of a topological space is as follows. Definition: let M be some set. And we know what a set is from axiomatic set theory. Then a choice, so you see you have a choice here, then a choice, and this choice is called curly O. What is this O? It's a choice, it's a subset of the power set of M. It could be the entire power set. So a choice of subset O of the power set of M is called a topology on M. So this choice is called a topology on M if, and now three axioms or three conditions need to be satisfied. The first condition is that you're not entirely free. Well, you're not entirely free in your choice. That's the idea of these three axioms. And one condition is that certainly the empty set, which is an element of the power set of any set, must be in your pick of topology. And likewise, the entire set must also be part of your choice. If you don't do that, you already have no topology chosen. The second condition is if you have two sets U and V that are already in your choice. So this, I want this one and that one. Well, if you did that, then it's a requirement that their union, that their intersection, very importantly, that their intersection is also in your choice. And you know that we had this funny way of writing unions in intersections, like the intersection, and then you need to provide an entire set that contains the sets you want to intersect. So, well, anyway, I first finish the statement. The intersection of these two sets is then required to be also part of your choice. You cannot choose U and V, but not the intersection. You have to choose that too. And in kindergarten, you wrote this U intersected V, and of course, if you wish, you can still define the intersection of, say, two sets here this way, but from the last problem sheet, we established this intersection in similar fashion to the union symbol, and the idea here is that you can only intersect, you could intersect infinitely many sets, not a question, but you cannot intersect more sets than fit into a set. Okay? Anyway, that's this here. And the third condition is if you have a collection of open sets. So here I took two, but now I take an arbitrary collection of open sets. Okay? Then the requirement is that the union of this arbitrary collection, not two, not finite, arbitrary collection, that this union again lie in your pick of sets. We could have written this in a more parallel fashion if I had written curly brackets around UV, that would then be a set, be a subset of O. If 2 lie in there, they build a subset of this set. Anyway. Right. So if these 3 conditions are met, then the pick you made, the choice you made, is called a topology. That's it. That's all. Now, before I elaborate on that more, let me make an important remark. Unless the set M only contains one element, there are many different, or there are different, usually many different, topologies O one can choose on one and the same set. So it's a real choice. And we can have a little table. So if the cardinality of the set M, so this is for finite sets, is 1, then how many topologies can you have? So it's the number of topologies one can have. Well, if you have 1, you can only have 1 topology, because you then always have to take the set M itself. It consists of just one element. That's this. You take the empty set, and there are no other choices you can make. But already if the set M has 2 elements, there are 4 different choices for the topology you could make. If the set M has 3, then there are 29 choices for the topologies you can make. If M has 4, you have 355 choices. If M is 5, you have 6,942 choices. If M is 6, you have 29527 choices, so 209,527 choices. And if the set M has 7 elements, you have 9,535,241 choices. And you see already for a 7-element set, it's an extreme number, right? And obviously, if you have an infinite set, there's an infinite number of choices for the topologies you could establish on that set. So it's a real choice you have, and depending on what topology you have, your notion of continuity and convergence, continuity of maps and convergence of sequences, which we're going to define solely in terms of the topology, will of course change. I'll present examples for that. Now, however, let's first start with basic examples for topology to get familiar with the concept, to become familiar. Well, let M be any set. On any set, we can choose the topology to consist of just the empty set and the set itself. Why is this a topology? Well, the first axiom is clearly satisfied. The second axiom, we have to consider whether the intersection of any 2 is again in O. The intersection of any 2 elements in O is again in O. Well, the intersection with empty is empty, is in there already. The intersection of empty with M is empty. Well, empty is already in there. The intersection of M with empty, well, that's symmetric, that's again empty. The intersection of M with M is M. Oh, but M is also already in there. That's the second one. And the third axiom is we have to see whether arbiters are again in there. Well, that's also true, because the only possible unions you can get are either empty or all of M, but empty and all of M are already in there, trivially. And so this is a topology. Topology. And this is for any M. And this topology has a name. It's called a chaotic topology. Why it deserves that name, we'll see in a second. You already guess it. It won't be very useful. It's only useful as an extreme example. But sometimes the extreme examples teach you a lot, as you know. Now, another extreme example is M be any set, and you can choose the, you can make a pick that you say, I take just any subset of M that is there. So you choose the entire power set. Is this again a topology? Well, obviously the power set contains any subset, so the empty set is in there, the full set is in there, first axiom. Or any two elements of the power set, the intersection is again, of course, in the power set, because the intersection of any two subsets is a subset, and the same is true for the union. The union of any arbitrary collection of subsets is, of course, a subset of M. Trivially, also a topology is a topology on M, and this is called the discrete topology. Discrete in the sense of separated, not discrete in the sense of, well, you know, the moral sense. Okay, so that's the discrete topology. And, oh, by the way, I should have mentioned, okay, so let's go back to this blackboard. The pair, it's just terminology, but it's important terminology. The pair where you have the set and you also provide a topology is then called a topological space. Called a topological space. And there you see the first real instance of what I very abstractly last time described as a space is a set with some additional information provided. In this case, a collection of subsets, or a choice of subsets of the set. So this is the second example here. This is the discrete topology. Now, in these two cases, we provided the topology by hand. Oh, I should also give, well, let me give yet another example, a very down-to-earth example. Maybe it should have been the first example. Let's take the set with 3 elements, 1, 2, 3. We know we have then a choice of 29 topologies, but we pick one of those. Well, at least we try. We choose as the topology, or the would-be topology, the set containing the empty set, we know there's no other choice, containing the individual elements 1 and 2, sets with elements 1 and 2, but not the one element set with 3. Then the set 1, 2, and the set 1, 2, 3, which is, of course, the set M itself. So, because of empty set and M being in there, first axiom is satisfied. What about arbitrary intersections? This with this is empty, this with this is this again, this with this is this again. Okay, not very helpful by me saying this and this is this again, but you can check, okay, any intersection already lies in there of any two, and any arbitrary union of those also already lies in there. So again, this is a topology, and this doesn't carry a name because it's not that interesting, okay? But it is a topology. You can find many others on 1, 2, 3. For instance, the chaotic one. For instance, the discrete one, and so on. Okay. Right. So these are these examples. Now, let me then come to the example that's probably most heavily used and that underlies the constructions on the real numbers we usually make for convergence and continuity, but in this case we have to, well, I guess it's just another example, but it's an extremely important example, important and heavily used example is the example where the set we are considering are the real numbers, or let's even take the real numbers to the dth power, which is, of course, just R cross Cartesian product R d times. That's the definition of RD, and you know what the Cartesian product is from our developments in set theory. Now, the question is, what topology could we equip the real numbers with? Well, for instance, the chaotic topology, or the discrete topology as extreme cases. But there is one very useful topology, and that's the following. And that's called the standard topology, O standard, on RD. Well, that's a funny name. And in contrast to the examples I provided so far, where I completely enumerated the elements I put into the topology, so I made a very explicit pick, the pick of subsets of RD that are then to constitute a topology is defined implicitly, because I have to provide overcountably many, at least in this type of definition. And so proceeds in 3 steps. So O standard is constructed in 3 steps. The first step is that you define an auxiliary quantity, and that is for every x in RD and every number r in R plus, so for every positive real number, you define an object called B of x sub r, and I first define it and then we interpret it. That's the set of all points y in RD, so of all d tuples of real numbers, such that the sum of yi minus xi in brackets squared, the sum from 1 to d, so I take all the components of this tuple, so this y is thought of as y1 to yd, this ordered tuple defined on the last problem sheet, discussed and defined. And then, for good measure, we take the square root out of here, and we require that this be less than the number r that appears here. So it's the x from here is in there, the r from there. It's for all y in RD, so it's restricted comprehension. We can do that. We define this funny set. Now, of course, this is usually written the norm of the difference between these tuples, and more precisely it's called the 2 norm, because you take squares of the differences and then you take the square root. You could also take a 2n norm, then you take here the power 2n, but then you also take the 2nth root, and then you got all of this in the 2n norm. You can make your pick of n for some n, and it will turn out, for the definition of the standard topology, it won't make a difference. And even if you take norms that cannot be constructed in this way, you know, they're funny norms, for any norm it won't make a difference what the resulting topology is. That's a famous theorem. But anyway, let's not be too general. Here we take n to 1. Okay, so we stay with the 2 norm, with the squared distance, and then the square root. Okay, we define these guys, and now how are we to think of them? Well, you already see this intuitively is the open, but that's just a name. It's the open ball of radius r around the point x in RD. That's the intuition, but it's just a set. I just defined a set. At this point, this has nothing to do with topology. It's just a quantity that's very useful. Now, the second step is that I now tell you how to decide whether a set U lies in the topology, in the standard topology, O standard on RD. And we'll say that U lies in there by definition if for every point P in U, if you look at this set, for any point P in U, there exists a number, a positive real number, r in R plus, such that the ball of such a radius r around the point P lies entirely within the set U. That's it. That's it. So that's the definition. Now, intuitively, this is like this. So let's take M to be R2. So I can draw a picture on the blackboard. And let's say the whole blackboard plane, infinitely extended, is R2. And now consider the following set. Everything that's inside this dotted line, but the points on the dotted line do not belong to the set. So the interior of this be the set U. Question, is the set open? Terminology. The elements of the topology are called open sets. That's why this is an O. Elements of the topology are called open sets. It's just a way of speaking which makes it simple. Okay, so U is an element of the topology, or U is an open set if for any point in U, so blindly I pick one, this one, there exists a positive real number such that the ball of that radius around this, and so I draw the ball, and this is also a dotted line, and the ball consists of all the points inside the dotted line. Why? Well, because that's exactly the statement. The distance, square root, for n equals 1, it looks like this, is less than r. That means it's really less. It's not less or equal to, then the boundary belong to it. It's less than r. Okay? So this is the n equals 1 case that we wanted to focus on. Now, if you pick any other point, even very close to this boundary here, that does not belong to it, well, you nevertheless will always find a radius such that everything, the entire ball, still lies completely within the set U. That's obvious. Now, if you had a part of the boundary at least that belongs to the set, it's not dotted, it's like this, then obviously you could choose as a point P that point on the boundary, but then no matter how small, but still positive, you choose R, no matter how small, you would always have a part here of that ball that does not lie within the original set. Then the set would not be open. Very clear, is it? It's very clear, right. Now, because it's so funny, the question is, how do the open balls in n equals 2 look like? So if I take the 4th power and the 4th root, that also provides a norm. You can check that. And so let me draw again the set U, or some set U. That's U again, another U. Now the question is, how do the open balls for n equals 2 look like? Well, they look a little bit like the screens of old TV sets. They're not square, they have still these round corners, okay? That's n equals 2. But still you see that yields the same topology, because for every TV set, if there's a point that has a TV set around it, you could have a smaller circle around, a smaller ball, but then for the smaller ball, you could also have a smaller TV set and so on. So what in the ball topology is identified as open is in the TV set topology n equals 2 also considered open, and the other way around. So it doesn't matter what n you choose. That's the intuitive picture for that. Now, if you choose n even higher, I don't know, 10,000, then the ball of radius r around the point P looks, at the distance you are, from the distance you are, it looks like this, but they're still a little bit round, these edges. And if you then take n to infinity, obviously you can't really do this, but if n gets bigger and bigger, you really arrive at these boxes. But no matter how big n is, every box contains a circle or a ball, and every ball can contain a box, and so on, and that then gives you the infinity norm, usually called the maximum norm, which can also be written more neatly without having infinities there with absolute values, but those are these boxes. But the topology built this way is always the same, so it doesn't matter which norm you choose. Okay, that's this thing. Well, now, I said it proceeds in 3 steps. Well, I still owe you the proof that this construction actually yields a topology. So, proof that this construction yields a topology. Proof that O standard RD is indeed a topology. So let's catch this. The first thing we got to check is whether the empty set is in there. Aha, how does this work? So I need to check, so I do this a little bit more carefully. Question, is the empty set in O standard? What do I need to do? I need to check if for all P in the empty set, it doesn't matter how this condition continues, because for all P in the empty set, we know that this is defined for all P for which P is in the empty set implies, agree? But P in the empty set is always false, because the implication arrow is defined with the principle, according to the principle ex falso quod libet, the whole thing is always true. And because this predicate is true for any P is a point now, it's not a proposition, therefore this is a predicate in P, the all quantor, the whole proposition, is true. That means, yes, it's in there. So the empty set is in the standard topology, ultimately because of the definition of the implication arrow. So the second condition we got to check, no, sorry, still the first condition. The question is M in O standard? The answer is yes, because, very quickly, the essential idea, well, the essential point is that any ball of any radius around any point in M is, of course, by definition, a subset of M, so any M is in there. So the second thing we ought to check is, if we got 2 sets in the standard topology, we need to check whether their intersection is in there. U intersected V, element of the standard topology, question mark. Well, the question is whether this is really implied. Now, let's start with the assumption U in the standard topology means for every, so we consider, I want to check whether this is in the standard topology. So I take an arbitrary point out of the intersection. What do I need to show? I need to show there exists a ball of some radius around this point that lies entirely within this intersection. How do I do this? Well, if I have a point in U intersected V, that means I have the point lies in U and the point lies in V by definition of the intersection. But then, because P lies in U and U is an open set, that means for every X in U, okay, do I need this? No, I can be quicker. I know there exists an R, a positive real number, such that the ball of radius R around this point P lies entirely within U, because U is open. But also there exists an R prime, or an S, also a positive real number, such that the ball of radius S around P lies in V, because U and V are open. But then immediately it's clear that the ball of radius that's the minimum of R and S, the smaller one, or one of the 2, if they're equal, around P, this then lies in both U and V. But that means it lies in the intersection. So we found a radius, we found a ball that lies in there. That means, because we took an arbitrary point out of the intersection, it means for any point in the intersection, this conclusion can be drawn. Hence, this lies in here. So indeed, this is correct. And third, well, we're not always going to go through all steps. It's just to demonstrate this once. Let's assume that C is some collection of subsets in O. So some set of sets in O. And the question is the union of C again in O? Well, that's very simple, because you pick any one set in C, let U be an element in C, then you know there exists, because this is U is then an open set, there exists an R in R plus such that B R, well, you know that for all P in U, there exists an R in R plus such that B R of P lies entirely in U. But then very clearly, it lies also in the union, because it already lies in 1. The union of all these C, because it already lies in 1, and this U is certainly a subset of the union. Very simple. That's it. So this implicit construction is, or provides a topology on the real numbers. Okay. Okay. I wanted to give this another section heading. Well, now I provide it as an example. That's fine. Okay, so then let's have 2.2. Construction. Excuse me, sorry. Let me see what I... Yes, that's fine. Okay. 2.2, construction of new topologies from given topologies. So once you have a certain toolbox, a certain collection of topologies, mostly new topologies that you custom design in order to solve your problem or to address your problem, are actually built from the building blocks you already have. So it's a very important technique to know how to construct new topologies from given topologies. And we'll start with the notion of a induced topology on a subset. So let M with O be a topological space. And let U, or let N, capital N, be a subset of the space M. Well, if the space M, let's say a proper subset of M. Then the following object, O stroke down N, that's a new symbol, okay, totally new symbol, is defined as the following set, is the intersection of U with N, N being the subset, for all U that lie in the topology I had on the bigger set, on the set M. Then this thing is a topology. Well, this is a theorem, a definition slash theorem, because there's the claim is this is a topology where on the subset N, and it has a name, it's called the induced, and sometimes one adds subset topology. Namely, obviously, it has been constructed from the topology on the bigger set by intersecting any open set on the bigger set with the subset, such that the entire O is certainly a subset of the power set of N. Any of these guys is a subset of N, clearly. Hence, we have a chance that this is a topology because it's a subset of N in the first place. So proof. It can be boring to go through these proofs, but I think for the first 2 or 3 definitions it's quite useful to get a feeling of how this works. So you always ask the same questions. You ask whether the empty set is in the topology induced on N. And the answer is yes, it is. Yes, since you can write the empty set as the empty set intersected with N, but the empty set is certainly an element of the topology on M, hence it's a U of this type, hence the whole thing is an element of the induced topology by definition, so the empty set is in there. Similarly, you got to ask whether the entire set N is in there. Yes, it is, since you can write the entire set N as N intersected N, as M, capital M intersected N. Capital M is clearly an element of the topology of M by the first axiom of the topology. But then because it has precisely this form, the whole thing is an element of ON, hence N lies in ON. First thing checked. Second, you look at the intersection. U, V, element of this topology. What about the intersection of the two? So you look at U intersected V, but you can, because these are subsets of N, because they lie in this topology, you can write them as U intersected N, intersected V intersected N, because they're already subsets of N, this doesn't change. Then you use here the associativity and so on, so it's U intersected V. Oh, I'm sorry. This was too quick. Obviously, I run into trouble right now. If I assume that U and N, okay, I wanted to squeeze it into this space, but you can't make a proof shorter only because the blackboard finishes. So let's be more careful. So obviously, if I assume U and V are in the induced topology, I first need to use the definition of the induced topology for the sets there, and then I can draw conclusions. Okay. So second, so assume U and V are in the induced topology. What we want to show or check is whether this implies that U intersected V also lies in the induced topology. Now, if UV are in the induced topology, this means that there exists in N. Okay, now I run into this trouble. There exists an S. You see, in order to not entirely confuse you and me for that matter, let's say we have S and T open sets, and we want to check whether the intersection lies in there. Now, what does it mean to be an element of ON? It means there exists a U in the topology on O, so that's the U up there, such that S can be written U intersected N. And T in there means there exists an open set V in the big space, in the topology of the big space, such that the subset T of the smaller space, of the subspace, I shouldn't say smaller, I mean subspace. You know, for infinite sets, it's difficult to say what means smaller. It's a subset to be precise. There is a V such that V intersected N gives you this space. That's according to the definition. Okay, so now then we consider S intersected T. But then I know S is U intersected N, and that's intersected V intersected N. And that is, of course, U intersected V intersected N. But U and V were elements of the topology of the space M, of the big space. I continue saying big and small. Of the big space. So this is an element of O. But you see, if something is an element, if you have an element of O intersected N, then according to the definition, the whole thing is an element of O sub N. So indeed, ST in O sub N implies that S intersected T is an element in ON. Okay, yeah.
Do you have shown that you're allowed to do the step from the first line to the second?
This here? No, we haven't shown that. You want it on the problem sheet? Okay, can do it, put it on the problem sheet. Yeah, but it's clear from kindergarten set theory. But I agree, there are many things you can prove. Yeah, that's true. That's true. So with our definition of the intersection, but obviously our definition of the intersection from the last problem sheet, in the case of finite intersections, fully reduces to what you learned in kindergarten with sets. Okay. Do you still do this today? That in elementary school, I say kindergarten, but in elementary school you do still set theory today? Or you did that in school? In the 70s, it was a big fashion, and people and parents got very unnerved because they said, "Oh my God, it's mathematics, I don't understand," and so on. But then it was cars and red cars and blue cars, and the intersection of red cars and blue cars was empty, stuff like that. Okay, good. And finally, of course, I'm not going to write this down now, is you check the third axiom that also arbitrary unions of elements in the induced topology lie again in the induced topology. So this is indeed the subset topology. So let's have one simple example. You can equip R with the standard topology. Okay? And then you can look at as N on N as what do I want to have? I want the closed interval. I use this school notation. You know how this is defined, of -1 to 1. Well, I mean, you know what set this is. Yeah? Okay, I define it. So this is the set of all x in R for which we have -1 is less or equal x is less or equal 1. Okay, so we have this interval. And now we can equip this set N, obviously, with O standard, but then induced on N. And my claim is, as an example, my claim is that the interval open 0 to closed 1, that doesn't look open, it has a point. If you judge this in the topology of R, this is a subset of R, so you can ask, does it lie in the topology? Is it an open set? You'll find it's not an open set because it has this point on the boundary. That's the argument from before, okay? But the very same set is also a subset of N. It lies in this interval, so it's a subset of N. And I can ask whether in the induced topology on N it's open. And in fact, it is open because it can be written as 0 to 2 intersected with -1 to 1. You agree on that? All right, so picture. No, you don't need a picture. Okay, so this is fine, this is this. But 0, 2 is an open ball. Well, it's open in the standard topology on R. Intersected, this guy is the set N. Aha, but any set that can be written as an open set in the bigger space intersected the subspace whose induced topology you consider is therefore an element of the induced topology on the subspace. So a set can be non-open in the big space, but nevertheless it can be open in the subset topology, in the induced topology on some subset, if it happens to be at the same time a subset of the subset. Okay? So it's always, the question is always, it's open with respect to what topology, even if this is a subset. So one must be careful not to draw too quick conclusions if one sees subsets in topology and judges the openness or not. Okay, so I just used the term non-open, and it's very tempting to think that non-open should be called closed. Well, you could, but you don't. So in topology, there's another convention in form of the definition. Let MO be a topological space, top space, and a subset C of M is called closed. Not if it's not an open, that would be, it's not the case. It's called closed if the complement of that set with respect to the whole set M is open. Okay, the complement is open. Okay, well, example, very quick example. The interval 0, 1 is closed in R equipped with the standard topology, not because it has because it has these endpoints. That just means it's not open, but it's actually closed because R without this subset, which is the interval from -infinity to 0 exclusively, because the 0 is taken out, union with 1 to infinity, exclusive the 1, because the 1 is taken out. Now, this set is open in the standard topology because for any point in there, you find a little ball that lies around it. The same is true here, but it's the union of two open sets in ON. So this is in O standard, this is in O standard, this is in O standard. Arbitrary unions, so certainly finite ones are in O standard. So this is in O standard, that means it's open. Because this is open, that means this is closed by definition. And so the warning is, a little warning sign, in general, that means if we know nothing particular about the topological space, so generic topological space for generic subset and so on, in general, a subset of a topological space can be A, open, B, can be closed, so or it can be open and closed, or 4, it can be open and not closed, or 5, it can be not open and closed, or 6, it can be not open and not closed. Meaning, being open and being closed has actually nothing to do with each other than via the complement. But you cannot see an open set and then conclude anything about its closedness, or you cannot see a closed set and conclude anything about its openness or in any of the other combinations. However, observation A, the empty set can always be written as M without M. That's right. Well, M is an element of, so observation, for any topological space, for any MO top space, the empty set can be written as M without M, but M lies in the open set, so M without M, obviously this is recognized to be closed. And B, M can always be written as M without the empty set, and for the same reason, well, actually this is open, hence empty set is closed, and down here this again is open because it's, hence the entire set M is closed, but because the empty set and M are also both open, the entire set and the empty set are of this type in any M', they're of this type. They're both open and closed. There's no contradiction. We'll later on define the notion of a connected topological space, and you can prove that in a connected topological space, the only sets that are both open and closed are these two. So if you find this funny that this happens at the same time, if you don't want this for some reason, you can look at connected topological spaces. Then these two are the only ones. But there's no topology in which this is not the case because it's a general property. Okay, so let me give you a real-life example where you use the induced topology. So assume you want a topology on the circle. So consider the set, first of all, a set S1. The set S1 is the circle. You all know what the circle is, okay? But I only think of the circle here as a set. So as a set, this is a circle, right? It has no shape. It will only get a shape once we have a geometry. Remember our building where only at the very end you have geometry? Only if you have geometry you can talk about that. Well, even this is already too much. It's already a continuous circle. Well, we're coming to that. But anyway, as a set, it can be understood, and you might find this... no, fine. You can define this as a subset of R2. That's one possibility. So you can say the circle is the collection of all pairs of real numbers for which x squared plus y squared is, say, 1. Okay, so if that's your definition, then in R2 it really already looks like this. Okay, fine. And now the question is, how do you establish a topology on the circle? Well, one way to establish a topology on S without starting from scratch is to let the topology on S, a topology O on S, is to define the topology as actually taking the topology, the standard topology on R2, and induce it on this subset. So how does that look like? So I could ask the question, the set that is here, the subset of the circle that's open, that has not this point, but also this point is not there, but all the other points in between belong to the subset U. The question is this an open set in the induced topology? What do you say, yes or no? Is this U open in the induced topology on the circle? Yes, right, it is, because there is this, well, I should call this S also, S, because there's this set U that's an element of the standard topology on R2, whose intersection with the set S yields exactly this set, right? Is the empty set, which is a subset of the circle, is that an open set in the induced topology? Well, we know that the empty set always is. Otherwise, I'd say the empty set on here is the intersection of this circle with this open set in the standard topology, okay? And the other question is the set that has one point, that consists of, say, just one point, it's a subset of the circle, is this one set point T? So T is this set. Is this open in the topology I established on the circle? No, it is not, because I cannot generate this point by any intersection of an open set in the standard topology out here and the circle, right? Because if I'm outside, that is not generated. If I just touch the circle, because the boundary of this subset is not there, it's not generated. And if I already cover it, then I cover more than one point. Very simple. So that's one way. And another way is to proceed entirely differently, namely to understand the circle as a quotient set. Well, last time we discussed equivalence relations and quotient sets. I can take the entire line and I only look at the equivalence classes of points where 2 points in the real numbers are to be identified by a relation twiddle, if and only if x equals, or y equals x plus 2 pi. Okay? So any 2 points whose difference is 2 pi on the real numbers are to be identified. That means you take the real line, you start with 0, but the point 2 pi is actually to be identified with the 0. Okay? And so you start again. So this way you get the circle as a quotient space, and you can then study how you inherit from a topology on this set a topology to a quotient space. I didn't show you how to do this, what the induced topology or the inherit topology on the quotient space is, but that will be on the problem sheet. Topology inherited by the quotient space, by a quotient space, is the problem sheet, a problem on the problem sheet. Okay. So you see there's sometimes several ways you can do this, but it's highly convenient to be able to build quotient spaces and to inherit topologies here, subsets, and so on. One more definition, a very important one, is how do you inherit the topology from 2 spaces A? So let's have a topological space A with a topology OA. It's now not the induced topology, it's just one topology, and let's have, because the induced one has this stroke there as well, and B with OB, let these be topological spaces. Now, very often you wish to have, you equip the Cartesian product of these 2 spaces. You do this all the time, implicitly. Equip the Cartesian product with the so-called product topology, which you construct in the following way. It's again implicitly given, so let's call it O down A cross B. It's the product topology, defined implicitly by U is an element of, let's call it W. Let's call U. U is an element of the product topology by definition, if and only if, for every point P in U, but you see, if it's a subset of the Cartesian product, so the point P can actually be written as a pair VW that lies in AB, as a pair AB that lies in A cross B. If for every P in this subset U of a Cartesian product B, there exists an S which lies in the open sets of A, which is an open set of A that contains A, and there exists a T in the open sets of B that contains B, such that their Cartesian product, such that the Cartesian product of these subsets lies entirely within U. So intuitively, let's assume we can represent A and B as this axis and this axis. Well, it's already a big assumption, right? Because topological spaces can look very crazy. There's no idea of even dimension in a topological space, right? That will come later. But intuitively, let's do it like this. And I can ask the question, is this set here, is it open or not? Well, if I need to check whether for every point, let's say this one, there is an open set in here, let's assume it looks like this, so I'm thinking real line here, and there's an open set here like this, because this point here is the AB point, it's the pair in this Cartesian product, and then I need to find sets S and T here, so this is the set, this entire thing is the set S, this entire thing here is the set T, such that their Cartesian product, which you can construct like this, so that's everything inside this dotted box, such that their square product, Cartesian product, lies entirely within the original set U, whose openness you want to check. And you see, well, this didn't quite work, but you can choose these two smaller around here, and then it may work or not. It depends on what topology on A and B you have, whether a set in the Cartesian product of A and B is open or not. I mean, this is very intuitively, this is inspired by standard topology, by A and B being the real lines in standard topology, this picture, but this is the picture to remember if you want to write down this general definition and check, can check, and I ask you to check on the problem sheet that this is a topology. This O provides, this OA Cartesian product B provides a topology on a Cartesian product B. And obviously, if you have it for for a pair, you can do it for any finite Cartesian product. So we have a remark. One can do this for any finite A1 cross A2 cross cross AN. And the second remark is that the standard topology, O standard, on RD, a bit too big this RD, on RD actually is the same. It doesn't matter whether you do this or whether you take the topology only on the real line and you consider the product topology of D times the real line equipped with the standard topology with itself. Why? Well, it's precisely the argument I gave with the maximum norm sub infinity before. It's because boxes always contain circles and circles contain always boxes and so on. Okay, so it's the same thing. So already for RD, you can understand so we could have been more minimalistic and defined the standard topology before only for the real numbers. And then we could have defined a topology on RD this way. Well, you can do it both ways and it happens to coincide. Of course, there's no a priori reason why it would, but in fact it does. Any questions at this point? Okay. So now, okay, before we continue, let me make one more remark. In this course, we always consider topologies as giving structures to sets, and finally we want to arrive at some manifold, some physical space, and so on. However, topology is not only useful in this, I say, roughly geometric context, where somehow you have to do with spaces that have to do like we imagined them geometrically. Topology is a very, very versatile subject, and hence it deserves its own status. And for instance, you can cleverly equip the integer numbers with a topology. Not a problem, integer numbers are set, there's certain topology you can establish. And so did a guy called Furstenberg. And Furstenberg discovered if I equip the integer numbers with this and that topology, which I choose in a certain way to suit my purposes, then you can provide an entirely topological proof, actually just thinking about closed and open sets, that proves that there are infinitely many prime numbers. Okay, so even in number theory, you can use topology as a tool. Well, so this shows the context in which we develop this as physicists maybe by far does not exhaust the applicability of topology. And so that's just a side remark. And this Fürstenberg example is a famous one because it's kind of unexpected that you can provide such proofs. And that, of course, goes a long way to explaining why we provide a definition of the form we did, of this abstract form. This is so abstract, it can actually cover a lot of situations. And then the brain work goes into choosing the right topology to solve your problem topologically. Okay, and of course that sometimes takes some ingenuity. All right, so that was the side remark. But anyway, whenever you have a topology, the whole thing is only useful if you can then actually do something with it. In this case, I provide this. It's the convergence of sequences and the continuity of maps. So let's start with the sequences. 2.3 convergence. Definition. A sequence, what is a sequence? That is a map, a sequence Q, that is a map Q from the integers into a set M, a sequence Q on a topological space M. So I need to provide the topology. That is a map that gives for every integer number a point in the set M that underlies the topological space. A sequence Q is said to converge against a point A in M if for every open set in M, for every U in O that contains the point A, that contains the limit point against a, well, let's call it limit point, so that's the definition here, if for every U that contains A, and this will appear very often, you saw this already before, we have an open set that contains a point. Very often one refers to this as an open, because it lies in O, an open neighborhood of the point A. Because A lies in there and it's open, and it contains it, so the U lies around it. What lies around you is the neighborhood. Okay, so that's just lingo, it's the terminology in topology. So if there exists an open neighborhood of the limit point, if for every, very important, if for every open neighborhood of the limit point, there exists an n in the integer, no, in the natural, sorry, it's not the integers, the non-negative integers, the natural numbers, such that for all n that are bigger than this particular n that exists, the images of the sequence of this map, starting from this n onwards, capital N onwards, lie in this open neighborhood. Okay, that's the convergence. Example. Let's choose a set M and equip it with the chaotic topology. You remember? That was the chaotic topology. So far, only a name. Now, consider any sequence. Let Q from N to M be some sequence. So you see, being a sequence has nothing to do with the topology. It's just a matter of being, well, this map into the set. But now if you have a topology, you can decide whether the sequence converges against some point. And my claim is any sequence converges against every point. So if you equip a space with the chaotic topology, no matter which sequence you give me, I can actually show it converges against any point in the space you provide me. Why is this true? Well, because what we've got to check is let Q be arbitrary and let the point A be arbitrary. I need to check whether for every open set that contains the point A, how many open sets do I have? 2. Which of these 2 can contain a point A? Only this one, right? So I need to check whether for every that contains A, so that means U is already the entire set M. Well, of course there exists an N such that for all n greater n, Qn lies in M, because for every n, Q lies in M because it's a map into M. Fully independent of what the point is, fully independent of how exactly the sequence is defined. So choosing the chaotic topology, every sequence converges against any point. Hence chaotic. Okay? That's the idea. And obviously it's not very useful. Okay? So if you are set an exam question, or if you're a teacher in the final exam, you're asked, show that this and that sequence converges, and the examiner is not careful enough to specify in which topology, you just claim, well, this sequence, whatever space on R, say it converges against every point because I choose the chaotic topology and you didn't ask me to choose any other. Okay, very quick exam solution. Similarly, you could look at M and equip it with the, yeah, I know I get into trouble with the others, but okay, and you can equip it with the discrete topology. What happens then? Well, then every set is open, and you see unless then the sequence finally is constant, so only all almost constant sequences converge, and if they converge again against the constant. What do I mean by almost constant? I mean Q of n always takes the same value apart from a finite exception set. Almost constant means constant everywhere apart from a finite exception set. You can check this, it's clear. And C, if you take M to be R and O to be the standard topology in R, then of course you have the theorem, you can prove that a sequence on R or on RD converges against A in RD if for every epsilon greater than 0, there exists an n in n, such that for every n greater than n, well, let's take some norm, it doesn't matter, of what is it, Q of n minus A is less than epsilon. Yes?
In the example B, is this not just the idea of convergence in the normal analysis way? You say if you find it out of a ball, then it's convergent?
Well, yes, because this is the finest topology. Everything that's convergent here would be convergent in any other topology. But in other topologies that are not that fine, where you choose not as many subsets, there will be sequences that converge in the other topology that do not converge here. Because you see, for instance, in this topology I'm writing down here, in RD, you could have a sequence, okay, example, so I choose the example according to that. You could have a sequence Q of n is given, so M equals R, so D1. Q of n is 1 minus 1 over n. Okay, how does that look like? N, yeah, okay, n with 0. and you start here from n, okay, n plus 1, okay, something like this. So you don't run into trouble with the 0 here, okay. And then obviously if this is the real line and this is 1, then 1 minus n is 0, 1 minus 1 is 0, you're here, and then 1 minus 1/2 is here, then 1 minus 1/3 is here, and so on. So you get closer and closer and closer, but this is not almost constant. Because every value is different. Okay, it's not almost constant. That is not convergent in R equipped with the discrete topology on R, but it is convergent in R equipped with the standard topology. So if you look at this and you say, well, it converges against 1, well, if you say, look, it does do so, you have the intuition of the standard topology, and that you have because the standard topology uses the norm or the distance, and our intuitive feeling about convergence is about getting closer and closer and closer. So if you can generalize this for every metric space where you have a metric map, you can actually construct from this metric distance function, you can construct a topology. But by far, not every topology is induced from a distance map. Okay? Okay, so that was the example there. That's convergence. Now we come to continuity. So let me make one half-serious side remark. If today you want to do research, you need to apply for money. If you want to apply for money, you've got to write a research proposal. A research proposal is of the type, we do this and that, because once we do that, we know more. Very fair. It's a fair thing. And in physics, you write, we come closer to the truth. Okay? Or in recent years, we have converged against the true theory or whatever you want to choose. Okay. So you write up this proposal, and and then it goes to several institutions. Maybe it needs to get the spiritual approval of the Office for Gender and Diversity. But once it has passed this, it actually goes to some experts, and they will read it, but the experts don't have time. So they just read the introduction, and in the introduction, it needs to say that we are getting better and we're making progress. Now let's half-seriously critically evaluate this. What does it mean, our theories in physics, for instance, make progress? One way you could express this, not the only possible way, but one way would be to say they get better and better. Well, better, you need a measure for whether one theory is better than the other theory. Maybe you know about non-commutative dice, right? So you can actually you can make dice, and you can distribute numbers on there like this, and then you can make another one. Well, look it up on the internet. Non-transitive. Why do I say non-commutative? Non-transitive dice, right? Non-transitive dice. You have a different distribution. Don't take the distribution seriously. It's just for illustrational purposes. And you have a third one. Okay. Now the claim is, and one can find distributions of scores on there, such that if this is dice A, B, C, that if A plays against B, and the rule is A throws the dice, B throws the dice, and then you look who got the higher number. Okay? Well, in some cases A will win, namely if B has 0, in all other cases B will win, stuff like this. And every time A has a higher number than B, A gets a mathematical number. B gets 1, then B, then A wins, and so on. Okay? So when you do this for some while, and in the end, after a long run, you determine who won by who got more strokes. Okay? And obviously, if there's a different distribution of numbers, possibly in the long run. I mean, you can calculate who gets with what probability what. Okay, so A plays against B. In this case, you would say, well, A, the quality of A, Q of A, was greater than the quality of dice B. If you want to play against this guy, you want this dice. Now, you can then let B play against C, and it could turn out, with the right distribution of numbers, that the quality of B is also bigger than the quality of C. Now, if you look at this, you say, if A, the dice A is better than B, and if dice B is better than C, then it makes sense that A is better than C. So A is the winning combination. And now think of this as research proposals, which usually are more complex than the distribution of such numbers on dice. You have more choices to make. But remarkably, there is a distribution of numbers on these three circles such that the quality of C is greater than the quality of A according to the rules I just gave. That means from Q of A being greater than Q of B, from Q of B greater, you cannot conclude this. Well, if you can't conclude this, that obviously means this quality measure doesn't exist. At least it's not real valued or something. Okay? I mean, this is remarkable. That means anybody who has the fantasy of assigning to complex situations like research proposals or the lovability of a girl or a boy, a real valued function that measures this for everyone and then compares on this scale. I mean, almost all of, what's it called? Economical science. Economics is built on this assumption. You can model things and measure the quality or the cost or whatever. Well, already something that's as little complex as the possibilities to distribute numbers on dice in such fashion doesn't have a quality function. So please nobody say this theory is better than that theory. You please ask immediately for the quality function, and very likely it's non-transitive, because generically it's non-transitive. It's only special distributions would then be transitive. Okay, that's the first thing. So you can't have a quality function in order to measure your research is getting better or your research you're proposing is better. But you might say, well, even if I don't have a quality function, I can still say it's coming closer to the true theory, how nature really is. Well, that would really be a very weak statement, but still impressive enough if it were true. But the problem is, in order to make any such statement, what would you need? You would need to know the topology on the space of all theories. That sounds like you can't write it down. Okay? At least I don't know it. So that means I assume, unless somebody convinces me by some other argument of the contrary, that any statement of the type, the theories are getting better, well, forget about this, the theories at least approach, converge somehow, well, you need a topology in the space of all theories. That's far too complex. So in that sense, because we don't know of any structure that can, by which we can define convergence that makes fewer assumptions than having a topology, topology also reveals nonsensical or ill-defined statements which sound good. It's a little bit like with the hairdressers and what hairdressers can do, only hairdressers can do in logic. In topology, maybe you can conclude, or at least this argument raises sufficient suspicion for any such claim. And of course, it applies to other circumstances as well. The next notion is continuity. And while convergence was interesting, continuity is at the heart of topology, because it will finally be used also to define structure-preserving maps. So 2.4, continuity. Definition. Let M, OM, and NON be topological spaces. And let phi be a map from the set M underlying the first topological space to a set N underlying the second topological space. then the map phi is called continuous. It's called continuous if for every open set in the target space. So you take an open set in the target space. If for every open set in the target space, the pre-image of this open set with respect to the map phi is an open set in the domain. Here. That's it. That's continuity. It's extremely simple. Maybe I remind you of the definition of the pre-image. The pre-image were all those points, M in capital M, such that, for which phi of M was an element of the specified set V in the target. That was the pre-image. Or, in brevity, phi continuous if pre-images of open sets are open. That hides the fact that this is the openness in the target space and this openness is the openness in the domain. So hence, more precisely, it's this condition here. This is at the heart of topology, as we'll see in a second. So examples, our favorite example is, one of the favorite examples, at least mine, is you start from a set M, you take a map between arbitrary sets, and you choose to equip this here, this set, with the discrete topology, and this set you can choose any topology you like. Question or claim, under these circumstances, with the target, with the domain and the target equipped with these topologies, any map phi is continuous. Why? Well, you choose any open set here, but the pre-image, well, it could be the empty set is open. What's the pre-image of the empty set? It's the empty set. Well, the empty set is certainly open. Okay. Now, you choose any other non-empty set. The pre-image of the non-empty set is a non-empty set. Well, not necessarily. It could be the empty set, but generically it's a non-empty set. It could be any set. It doesn't matter. I shouldn't have made this distinction of cases. So again, take any open set here. The pre-image is certainly a subset of M, but every subset is open. That's the condition. It must be open. Hence, any map is continuous because I didn't use any particular properties of the map. In other words, once you equip the domain with the discrete topology, continuity is clear. It's simply there. Every map is continuous. Well, if every map is continuous, continuity becomes a useless property. Hence, you never equip the domain with the discrete topology if you still want to work with continuity. It's the first example. The second example, you take the map from M to N. Now, the domain, you can choose anything you like. In the target, you choose the chaotic topology. Similar game, any map is continuous, as you may quickly think about. And then C, you take a map from RD to RF. You equip both of them with the standard topology, respectively, and you recover the standard definition of continuity on from maps from RD to RF. So for every epsilon greater than 0, there exists a delta greater than 0, such that for all x minus y, and so on. You know how that works. It's the epsilon delta criterion for continuity is recovered from this very general definition of continuity for every topological spaces or pair of topological spaces in the case you equip RD and RF with the standard topologies. Yes?
Should that be an N instead of an M in your topology?
Where are you? Here, that's an N. You mean this? Thank you very much. Yes, of course, it must be N. Thank you. Okay. So we have this continuity. Now, we have another definition that is, let phi from M to N between two sets be a bijection. A bijection is, of course, a bijective map. Let this be a bijection. Now, equipping M with OM and N with ON, so making topological spaces out of these sets, we call a bijection phi a, and that's the central notion of map in topology, we call it a homeomorphism. A homeomorphism if both phi from M to N, now being topological spaces, is continuous, and B, the inverse of phi, going from N to M, and the inverse exists and is unique because M is a bijection, phi is a bijection, is also continuous. And remark, homeomorphisms, and usually we write homeo and then the morphism part we suppress because it's a long word. Homeos, meaning homeomorphisms, are the structure preserving maps. Preserving maps in topology. Why is this? Well, you go from M to N and you go back. So phi takes you from M to N as a set, and phi inverse takes you back. Now, if phi is continuous, that's one of the conditions, then the pre-image of any open set is an open set. But the pre-image is just the image of phi to the minus 1, because it's a bijection. The other way around with the phi to the minus 1. That means by having a homeomorphism, if a homeomorphism exists, definition, if there exists a homeo phi, that's this picture, then phi provides a one-to-one pairing of open sets of the open sets of M with those of N according to the chosen topology. So you can say the topologies are the same, have the same structure. And we then write, in case a homeo phi exists between two spaces, topological spaces, we say that this topological space is isomorphic to that to that topological space, but it's isomorphic in the topological sense. So we write the same isomorphism sign as we did in set theory, but now it's not only as sets they're isomorphic, they certainly are because there exists a bijection between them. Remember, existence of a bijection means as sets, ignoring the topology, they're isomorphic. But it's even more, even if you equip them with topologies, but now the map, the bijection, has to satisfy an additional condition, namely this homeomorphism condition, then they're even isomorphic as topological spaces, isomorphic as topological spaces. That's very long, so people also say homeomorphic. Homeomorphic. So a map can be a homeomorphism, but two topological spaces between such a homeomorphism map exists are called homeomorphic. Okay? And obviously, topological isomorphism or homeomorphism implies that the underlying sets, set theoretically, are isomorphic. That means you can have two sets that are isomorphic, but then you equip them with topologies, and as topological spaces, they become non-isomorphic topologically. We could say topologically that they'll be different. Okay? And that shows you added structure, and things that are the same or isomorphic, that means same up to some reshuffling, can, by way of establishing different structures, become non-isomorphic at a higher structural level. Perfectly fine, right? I have two children, they're both blonde, but now I dye their hair, and one is blonde and the other is red-haired, now they're different, okay? Well, one finds other distinguishing properties, but okay, fine. So that's this, and so as structure-preserving maps, and you remember the general dictum that the recurrent theme, or one of the recurrent themes in mathematics, is that you classify spaces by considering structure-preserving maps between them. Now, in set theory, well, I only hinted to that, but in set theory, you define sets by their you classify sets by their cardinality. We didn't go very far there. There's a very big theory behind that. But finite sets, you classify by the number of elements. If two finite sets have the same number of elements, they are isomorphic as sets. Then they can be finite, countably, and so on and so on. Okay. Now, for topological spaces, one would like to find properties that also distinguish topological sets in the sense, and we're going to define such properties. Well, let me first define such properties, and then I'll come back to this point. But I tell you already, nobody knows a complete set of properties of topological spaces, like in set theory, number of elements, okay, roughly speaking. For topology, nobody knows a complete set of properties such that you could check all those properties for one space and for the others for another space, and then say if the set of these properties is matched for both topological spaces, then the topological spaces are already homeomorphic. Right? One would like to have such criteria. There exists no such criteria, and hence one says there exists no classification, at least nobody knows of any classification of topological spaces. There are just too many, or we haven't thought carefully enough, but that's an open classification problem, as far as I know, but I think that's correct. So, yeah, you can prove that and then make donations to the university. It's always important to know what the open problem in a field are, because if you want to solve some of them, you better know they're open.